Hello everyone, my name is Irene and Tiago and myself will be presenting to you today our joint work with Kyle, Ryan and Damián titled How Non-Optimal is the Lexicon. So there's a fairly long history of research around the optimality of language. For example, Zipf's law of abbreviation can be seen as a sign of language speakers seeking efficiency. However, it's not very difficult to come up with counterexamples to this law, such as short but low-frequency words. In our paper, we take a different standpoint. We're actually interested in the non-optimality of language. So we want to see just how far is language from its information-theoretic optimal. And also we want to study the different processes behind this distance. So in practice, we want to be able to place natural language on a line of code length, where on the one end, the codes are created by an optimal model, and on the other, by random mappings. And this also allows us to map out the effects that different constraints have on the optimality of a language's code lengths. This is actually a sneak peek to our results. It's for Finnish specifically. So we adapt a coding-theoretic framework. We look at meanings as messages, words as codes, and listeners as receivers. So this means that Zipf's principle of least effort will indeed decrease the expected code length of a language, since frequent messages are encoded in shorter words. However, a language that's purely optimized for code length would look very different from the languages we actually see in the wild. This is partly because of phonotactics, which limits the sequences of speech sounds allowed in a language, making words pronounceable and then also giving a language its own characteristics. On the other hand, morphology will allow subparts of words have their own meanings, which can then be used productively to create new meanings. And this kind of internal logic will also make language more easy to learn and understand. And these are the two things we want to study the effect of on code length. Now, how can we do this in practice? So we have meanings which have their own inherent frequencies, which we can then model with the unigram distribution. And then each meaning has a set of possible codes. For example, here is the Finnish code for the meaning cat. Now, once we have a model for the meaning distribution, we can then calculate the expected cost of a code. This actually means that we have two challenges. The first one is to model the meaning distribution, and the second one is to find the optimal codes with minimal cost. In practice, we make a simplifying assumption that there's a one-to-one mapping between meanings and word forms. Now, this is obviously not true in the real world, but it makes our task feasible, since it means that we can actually just model word forms as meanings. Now, we could technically just model word forms using a character-level language model, but because word frequency follows a power law distribution, this kind of model would be likely to be biased towards the small subset of words which dominate the corpus. Luckily, this problem has been addressed in the past, notably by Goldwater in her 2011 paper. We actually take her model and add a neural net component to it. So her model consists of two components by and large: a generator that models word forms and an adapter that models word frequencies separately from the generator. So in our case, the generator is an LSTM character-level language model, and the adapter is a Pimentel Chinese restaurant process. And using the Pimentel Chinese restaurant process actually allows us to retrain the LSTM using a new corpus where word frequencies are more balanced, and this should result in a language model that's less biased toward the most frequent words. Just as a note, we end up modeling graphotactics instead of phonotactics because we use written language as our data. So in the end, this gives us a marginal probability of a word form consisting of smoothed unigram frequencies encountered in training and the word form probability provided by the LSTM. And this means that for more frequent words, the smoothed unigram frequency, part of the probability will have a bigger effect, and thanks to the interpolation weight for less frequent words, the LSTM word form probability will have a larger effect. And this means that we'll be able to model both frequent and infrequent words well.
Hi, I'm Tiago, and I'll take on the presentation from here. So now that we have access to this estimated meaning distribution, we can go forward to get the length of the codes we're looking for. And we start with presenting the equation for the expected code lengths for any code. And we see this is basically the expectation of the length of the code for a specific meaning taken with respect to the meaning distribution itself. And we can get a simple estimate for this on held out token data by using simple estimates instead. And for this, we just sum the code lengths we find for the word tokens from 1 to n. And we can use something like Wikipedia, since we assume that word forms and meanings have a one-to-one relationship. So we can map directly the natural word forms that we find in Wikipedia to the meaning they represent, under our assumption at least. So moving to the natural code length, we can take it with this equation. And this is simply taking the average word length across all the tokens in this corpora. We now move on to the optimal code length, which we take with this equation. And this is actually an expected upper bound, since we're using a sample estimate and since we're using the length of the codes that Shannon gave in his classical mathematical theory of communication paper. And we see that we can take the length of any code by this by approximating it with this log of 1 over the probability of that word form, and this will give us an upper bound to the optimal code. We're also interested in morphologically constrained codes, and for this, what I do is we rely on Morphessor to get subword units for our corpus for each language. And we take those subword units as a proxy to morphemes. Then we can train the same meaning distribution model from before on this morpheme level, assuming the morphemes themselves are the unit with an inherent frequency in language instead of the full word forms. And then we can take the expectation of that with relation to a word token. So we sum the code lengths for each individual morpheme that composes a word. We now move on to our graphotatically constrained code. And for this one, what we do is we sampled words from an LSTM, and we use our previously trained generator for this. We assume that since our generator is an interpolation between, trained on an interpolation between types and tokens, it will be better at modeling the graphotactics of a language than either a type level LSTM or a token level LSTM by itself. And we actually have another paper coming on ACL findings talking about the challenges of modeling a unigram distribution and why it's important. So feel free to check it out. But now that we have these sampled words, we can compute the code length for this graphotatically constrained code using these sampled words. And what we do is we simply pair the shortest sampled word form with the most frequent word token in our corpora, making a perfectly Zipfian distributed alignment. And then we can take the expected word length for the sampled words across the tokens. And finally, the last code we're looking at here is this morphology plus graphotactics code, which follows both constraints. And for this, we basically combine both approaches before. We first split words using Morphessor, then we sample morphemes themselves from the LSTM. And then we compute the code length using the sampled morphemes. And we note again that we take the expectation per word. So we sum the lengths of the individual morphemes that compose it. So moving on to our results, we find that all the analyzed languages follow the same optimality order, in the sense that if we sort the codes based on their length, we get the same order across all the analyzed languages. We also find that graphotactics yields longer codes than morphology across the board, which is interesting, in our opinion at least. And that natural code is longer than the code with morphology plus graphotactics for all the analyzed languages as well, which serves as a good sanity check to see if our codes are actually being optimized. We further find that all languages are close to random than to a pure optimal. And what is more interesting, at least in my opinion, is that for most languages, the morphology plus graphotactics accounts for most of the natural code length. So it seems that morphology plus graphotactics are responsible for most of the word length that we find in natural languages. And we conclude here that we can use coding theory to analyze the lexicon's efficiency. We find that lexicons are more efficient than random, but far from optimal, and that morphology plus graphotactics can explain most of the natural language's code length. So thank you for watching our presentation, and we'll see you in the question answering session.